Hi, this is Huda Zenhom from Physics 2212, Section P, and this is the fourth lab of the semester. To introduce, the purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, to examine the behavior of ohmic resistors and capacitors. So the basic procedure and setup, first we go to the circuit construction kit in PhET and construct the circuit system that includes resistors, ammeters, and batteries, and we can see that the values of them and the placement of them are shown on the right. So some concepts to consider: the loop rule. First, we have that all potential differences equate to zero, the sum of them. And then we have the node rule, the sum of the currents flowing into this node equal the sum of currents flowing out of the node. And we have the capacitance formula, charge over delta V. And we have Ohm's law, which is that V equals I times R, or some variation of that. So for our predicted current, we consider Ohm's law, as stated before. So I equals V over R, and our volts, which is 3 volts, combining the volts of the batteries and combining the ohms of the resistors of 147. This is about 0.02, and we can see once we simulate it, we get the same thing. And when the current when the ammeter is reversed is negative 0.002. So same thing, but just reverse sign. So for our broken system, now it's replaced with the voltmeter, one of the ammeters. Then the circuit is open, so the current stops flowing. The voltmeter reads negative 3 volts, meaning that the potential difference is the opposite sign of the voltage of the batteries when circuits are open. For our circuit path, we can see from the loop rule that the sum of all points from A to H around the circuit should equal to 0 volts. And it does, because from A to B it's 3 volts, from C to D it's negative 0.96 volts, and from E to F it's negative 2.04 volts. Everywhere else it's 0. So when we add all these values up, we get 0, confirming that the loop rule is correct. When ammeter is parallel to resistor, we place an ammeter parallel to the 100 ohm resistor, and then the resistance cancels out. From Ohm's law, we can see that the current and resistance are indirectly proportional. So when one value goes up, the other goes down. And then we have I equals 3 volts from batteries divided by only the 47 ohms resistor. That's the only resistor now we have to consider, since it's canceled out the other one. Then we get 0.063 amperes. For our RC circuit, we have to create a circuit system now that includes a 9-volt battery, and then we have a capacitor of 0.2 farads, and then we either have a 10 ohm light bulb or a 20 ohm light bulb. So when we connect the capacitor first to the 10 ohm light bulb, as time increases, the bulb dims until it fully switches off. Then we can disconnect the battery and connect the capacitor to the light bulb again. The bulb is bright at the start. The current flows in an opposite direction now, and the bulb dims until it loses light completely as time passes once again. So for our capacitor discharge time, for the 10 ohm one, we have 10.5 seconds for charging and then 14.5 seconds for discharging. And the 20 ohm one, we have 21 seconds and then 29 seconds. This is basically double the time for double the amount of ohms. Now for calculating our capacitor time constant, when we manipulate this form of the potential difference formula, we see that the slope is negative 1 over RC. And this seems to be true because when we plot our data, we can see that it is negatively downward sloping, and that we're plotting ln of V over V naught over time, and it is less steep because of that fraction that's going on. So some questions to consider. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? A real ammeter wouldn't have an ideal resistance of 0 ohms. It's not possible to just have completely no resistance at all. So this calculated current would have a lower value. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? In the PhET lab, the capacitor got charged within an instant, where in real life, the components of the system have some sort of resistance to them naturally. See, just as stated before, everything naturally has at least some sort of resistance, even if it's in a small quantity. The capacitor would charge and discharge at a slower pace because of this. Thank you and have a great day.